You are given a string that contains of opening and closing brackets, and you have to find the longest substring that is a valid parenthesis. How do you solve this problem? To solve this problem, first let us look at the structure of some valid parenthesis. Consider this valid parenthesis, which is an opening and closing pair. If you append another opening and closing pair, this is also one valid parenthesis. Instead, if you consider this scenario where you have a nesting depth of 2, this is a valid parenthesis. But then if you append another valid parenthesis over here, then this also creates a valid parenthesis. In fact, you can see that any set of valid parentheses can be appended together to create a new set of valid parentheses. For example, you see that has a nesting depth of 3. This has had a nesting depth of 2. And if you concatenated them, it gave you another valid parenthesis which has 2 different nesting depth. And you can see that this is true for any kind of valid parenthesis that exists. For example, this is a valid parenthesis. This is also a valid parenthesis, and any concatenation of these two is also a valid parenthesis. So let us formalize this statement. So we say that concatenation of two valid parentheses is a valid parenthesis. So this is our first claim, that concatenating two valid parentheses will give you a valid parenthesis, which is the easy part. This part is very trivial to see. You can see that if you have this valid and this is also valid, their concatenation will also be valid. But what is not obvious is that it is also true the other way around. That is, any valid parenthesis is a concatenation of valid parenthesis. And this idea, it's not that difficult to prove. In fact, this comes from kind of the definition of valid parenthesis, but the solution that we'll talk about in this video relies completely on this fact that any valid parenthesis in the world is a concatenation of some valid parenthesis. Now you can try to draw some examples on paper and you will realize why this statement is correct. But let's assume that this statement is true, and let's talk about how you would solve the problem of finding out the longest valid parenthesis in a string. So let's assume that you have this string. So if this is the string that is given to you, then the longest valid parenthesis, of course, it has to be a substring because we are only interested in the substring, not a subsequence. So this is the substring that you are interested in, and assume that without loss of generality that this is the substring that is the longest valid parenthesis. Then of course this substring has to end somewhere. This is the location that it ends at. We do not know which location this is, but we know that it has to be some of these existing location. So if we define a dynamic programming something like this, define dp of I as the length of the longest valid parenthesis that ends at index I. This is our dp definition. That is, we don't know what the optimal ending position of the longest valid parenthesis is, but if we try out all the ending position as one of the possibilities, then we would have our answer for sure if we take the max of those. Now let's see how do you populate these dp values. So if suppose this is the index I that you want to find out the DP value for, and suppose this index is an opening bracket. Then if this is an opening bracket, then of course no valid parenthesis can end over here. Why? Because since it is a concatenation of valid parenthesis, the last character has to be a closing one. So one thing you know for sure, that dp of I would be equal to 0 if str of I is equal to an opening bracket. But what if it is a closing bracket? So if this is a closing bracket, if this is a closing bracket, then you know from the previous slide that this string can only be formed by a concatenation of some valid parenthesis. So then if it is a concatenation of the valid parenthesis, then if it ends at index I, if this is the index where it ends, then we ask ourselves where can the last, so if it is a concatenation, then this would be one valid parenthesis, this would be another, this would be another, and so on. This would be another, and this would be the last valid parenthesis that ends at I. So then we ask ourselves, okay, what is the last valid parenthesis that was concatenated? And then once we locate the position of the last valid parenthesis, you can see that since this is a concatenation, then you are interested in that same question but on a smaller array. That is, you want to find out what is the longest valid parenthesis that ends at j minus 1 index, where j is the index from which this valid parenthesis, the last valid parenthesis starts, or let's call it as L. So if you call it as L, then you are looking for the L minus 1 DP value. So how do you figure out what is the last concatenation? So to do that, you can notice that if the element at str of I is equal to a closing bracket, then you just have to traverse to the left, and if you find an opening bracket like so, then you can see that this is the last concatenation, because you have just found out the longest valid, you have just found out the last parenthesis that was appended. So you can see that if this is your index I and if this is your index L, then you can see that the length would be 2 plus dp of L minus 1. But what if you don't find an opening bracket over here? Then the other case could be something like you encounter a closing, and then you encounter a closing bracket again, and after that you encounter an opening bracket. But this opening bracket that you have just encountered, you don't actually have to stop over here, because you are looking for the matching pair of this one, so that you can create a valid parenthesis. But this is a matching pair for this. So you have to keep on going, and now suppose if you find something like this, then you can see that this matches with this, and then this entire bracket set that you see, this is, you can say that this is closed. So this is closed. It means that all the opening and matching pairs are present inside this bucket only. So you can define it as a cover. Cover basically means that for all the closing brackets that you have, the corresponding opening bracket should also be in your cover. So if you find this, then if this is your index I and if this is your index L, then your answer would be 4 plus dp of L minus 1. Similarly, if you continue this reasoning, you can see that you want to find the cover that contains this. But then if you encounter another element that is closing, you also want to find the cover that contains this as well. Then this. So suppose you encounter a nesting depth of 3, then you can see that when you come across this element, then this entire subarray of length 6, this is actually a cover because every element has a matching pair here. It has a matching pair and it has a matching pair. So if this index is I and if this index is L, then your answer would be 6 plus dp of L minus 1. Why? Because this is the last valid parenthesis that you must have concatenated, and if that is the case, then you want to extend this part as much as possible. And similarly, you can also look at the another example where you have something like this. You have 4 closing in a sequence and then you have 4 opening like so. You can see that when you are traversing from right to left, you are interested in the cover that contains the opener for this closing bracket. But then you also included this element in your cover, so you are also looking for the opening bracket for this, and then the opening bracket for this, and then the opening bracket for this. And then you can see that you already match the opening brackets like so. You match the opening brackets like so. So once all the brackets have been matched, the string that is generated is called as a cover. And you can see that once you have reached a cover, and if the starting index of the cover is L and the ending index of the cover is I, then your answer would be 8 plus dp of L minus 1. So in general, your answer would be cover of I plus, sorry, it would be, you define L as cover of I, and your answer would be I minus L plus 1, which is the length of this cover, plus dp of L minus 1. So this is the simple dp transition. Now all that remains is how do you efficiently compute the cover for each index, for each element in the array. And cover is basically the smallest substring to the left that has the matching pair for each of the closing brackets that you have encountered. And this part, you know that you can simply do it by stack when you traverse from left to right. So when you are traversing from left to right, you simply, if you want to find the cover for each of these elements, so you can see that whenever you encounter an opening bracket, you put it on the stack, you put it on the stack, you put it on the stack, and then when you encounter a closing bracket like so, then the element that it pops from the stack, that will exactly be the cover of this element, because this is the point where a matching pair was discovered. So this cover is nothing but cover of I is the element that I popped from the map, popped from the stack. So let's look at the implementation for this. So first of all, we want to find out the cover for each of the closing brackets in this string. So we iterate the map, and suppose this is your string. Then let me show you an example code walkthrough. So if the index is 1, 2, 3, 4, 5, 6, 7, and 8, then as soon as you encounter an opening bracket, you push it onto the stack. So you have pushed 1 onto the stack because 1 is an opening bracket. Then you have pushed 2 onto the stack because 2 is an opening bracket. Then when you see a closing bracket, you have to pop from the stack because you have just found a matching pair. But since 3 is popping 2 from the stack, you can see that this 2 is a cover for 3. It means that this string 2 comma 3 is a balanced or a valid parenthesis, and then you can remove this 2 from the stack. Then when you introduce 4, you see that 4 will pop 1 from the stack. It means that the cover for 4 is actually the first element. It means that this 1 comma 4 is a valid parenthesis, and this is the minimum length of the valid parenthesis that you need that includes this element at index 4, and then your stack becomes empty. Then you repeat this process, you add 5 to the stack, and then you add the index 6 to the stack, and then when you encounter the seventh element, which is a closing bracket, so this seventh element, it will pop this sixth element. So whatever element you are popping, that is your cover. So 6 comma 7 is one cover, and then this has gone from the stack, and then when you insert 8, 8 will pop this 5. So you can see that 5 comma 8 is one cover. So now you have the cover for each of the closing brackets. So then you have to just apply a simple dynamic programming where you have this string, you iterate from left to right, or in any order is fine. And then you see that if it is a closing bracket, if it is a opening bracket, of course nothing can end at it, right? Because our definition is dp of r is the longest valid parenthesis that ends at I. So if it is a closing bracket, you just have to find the cover. Suppose the cover is over here, then you see that this string from L to I, since that is a cover and cover is a valid parenthesis, and the length of the cover is r minus L plus 1, and then you have to extend this to the left as much as possible, since every valid parenthesis is a concatenation of covers. So that's why you add dp of L minus 1, and at the end, whatever is the maximum length of any substring that is valid and ends at I, that is your answer. And the benefit is that with this you could also find out how many substrings. So if this maximum is m, that is the longest valid parenthesis is of length 20, then with this dp definition you can also find out how many strings actually achieve this length 20. And what would that be? That would simply be how many dp values are equal to 20. So if you want to solve this problem, I will link down the problem statement in the YouTube description. You can check it out. So this was one of the problems that involved very simple dynamic programming. And if you know about the basics of the stack method that is used in valid parenthesis, this is not that difficult to solve. But either way, I think this is a good problem to solve as a beginner for one dimensional DP and longest valid parenthesis.